Okay, returning to the problem that we were working on, we have the shipment of batteries claim that the population average life is 120 hours. For a sample of size 36, we created a decision statement or decision rule over here on the upper right hand corner. And we are going to reject the null hypothesis if our sample of size 36 yields a sample average that's under 116.71. We will accept the null hypothesis if the sample average from that sample of size 36 is greater than 116.71. Now what we're investigating here is our type 2 error probabilities. In other words, the null hypothesis is incorrect, so that would mean that the population average is something less than 120. And what would be the power of the sample ultimately to correctly reject various values under 120? Now suppose the population average is 112. In reality, it really is 112. The sample of size 36 would end up accepting the null hypothesis, or leading us to accept the null hypothesis, about 1% of the time, which is pretty acceptable risk level. In other words, there's a 99, almost 100% chance that we would correctly reject the null hypothesis if the real population average was as bad as 112. Suppose the real population average is 115. Then the probability of accepting the null hypothesis goes up a little bit to about 19.5%. So the closer we get to 120, the higher the risk is in making a type 2 error. The sample average would end up causing us to reject the null hypothesis about 80.5% of the time. In other words, the power of the sample size 36 to correctly reject the null hypothesis about 80.5%. Now I went ahead and done another level here with the population average. Suppose it's 117, and calculating a z-value for the 116.71. We find that our probability of type 2 error goes up to about 56%. And that is very unacceptable risk under normal circumstances. So our sample of size 36 is not very powerful, about 44.1%. It's not very powerful to correctly reject the null hypothesis, and we have a lot of probability there that we'll end up accepting the null, and the null is wrong. If the real population average is 117, the null is wrong, and there's a good chance we'll accept it by a sample of size 36 under that decision statement. Now I want to go ahead and calculate another one here for you. Suppose that the population average is as high as 118. Then we will find beta, the probability that we will accept the null hypothesis under the decision statement. Notice the decision statement says we'll accept the null when the sample average from our sample of size 36 is greater than 116.71. So again, what is the probability that that we will make a type 1 error, that we will reject? Well, it's the area under the curve of the density function for the sampling distribution above the 116.71 mark. And how to calculate that? We have to find a z-score for the 116.71 in the condition that the real population average is 118. So I want to subtract there and divide by my standard error, and I get a negative 0.645, which I will round to a negative 0.65. And the table value, table always reads down to the left. The table value turns out to be 0.2528, And our beta value then, our probability of making a type 2 error, is 0.7422, about 74.2%. Again, very unacceptable type 2 error. Now, if I look at all this in my little analysis here and investigating different values of the population average under the type 2 analysis, I see that the sample of size 36 is really going to be powerful for averages, population averages down as low as 112. But as we climb above that, we could see that our probabilities for type 2 error increase quite a bit. Now, it would be interesting to investigate values for 113 and maybe 114. Now, the table below on the Angel webpage there says that the 114 gives us a beta value of 0.0869. In other words, a type 2 error probability of about 8.7% and a power of 91.31%. That's still somewhat acceptable. But let's go ahead and calculate for 113. So I'm going to go over here to the right. Let's see what the probability of accepting the null hypothesis is if the population average is as bad as 113. So I'm going to go ahead and get a z-value here, and it's 1.855, which I'd round off to 1.86, and I get a 0.9678 table value. So beta would be 1 minus 0.9678, or about 0.0322. So that's about 3%. Usually our risk levels are around 5% or lower, so that would also be, the sample of size 36 would also be pretty sufficient in rejecting this shipment if the average was as bad as 113 hours. But if you get up to 115, as I've calculated there on the left, 116, 17, 18, if you look at that chart below on the web page there, you can see that the power drops off pretty quickly once you get up to or beyond 114. So our sample size 36 is really sufficient for correctly rejecting the null hypothesis if the actual population average is as bad as 113 or less. Now, that may be fine if you are the person purchasing this shipment, if 113 hours, if it's as bad as that, but that's still acceptable to you, you're in great shape with a sample of size 36. But let's say that you're pretty picky about this and you want the population average to be at least 118 or 119 hours when they've claimed it's 120. Then a sample of size 36 isn't really going to protect you in making the correct decision. You're going to have to increase your sample size. As you can see on the chart on the web page there, that the power of the sample of size 36 drops off pretty quickly, again, after the 114. But the time you get to 118, it's down to about 26%. So what we would have to end up doing is to get a larger sample. It turns out that the way to control both type 1 and type 2 is through sample size. We would have to get a larger sample. In the next section, there is a procedure that we can use to calculate what that large sample will need to be to satisfy our error requirements. Now, a little further down the page there is a problem for you to try. Given a sample of size 100, in other words, increasing from a sample size 36 to 100, go ahead and calculate or put together a decision statement and use that decision statement to fill in the chart. calculate the type 2 error probabilities for the different values of mu and the corresponding power percentages, and see how powerful, quote unquote, that sample of size 100 is to correctly reject the null hypothesis for those different values of mu. Compare your results from this table to the one that I helped you fill out and see what the differences are. Let me know if you run into trouble or have any questions.